Medical AI looks deceptively simple in the demos, right? You see a quick screenshot of a chest X-ray JPEG, you ask a question, and bam, you get an answer. It feels easy.
But then you hit the reality of a production pipeline, and that ease just evaporates. Suddenly, you're not dealing with a simple image file.
No.
You're handling a high-dimensional CT volume with 300 slices, or a whole slide pathology image, a WSI, that's gigapixels huge. That's the moment your budget, your patience, and often your server's memory just follows a massive complaint.
Absolutely. The jump from academic demo to real-world complexity is immense, and that's precisely why we're zooming in on MedGemma 1.5 today. It's an open-source model designed specifically to bridge that yawning gap.
Yeah, it brings complex, high-dimensional medical imaging much closer to the standard local developer workflow.
So our mission today is really custom-tailored for you, the person who needs to get this running now.
Exactly. We're going to provide a clear, practical map of MedGemma 1.5's capabilities, its necessary guardrails, and, the exact steps you need to run it safely and locally. We want to take you from just being curious to actually having a working prototype.
Efficiently and without that recurring cost of cloud APIs.
That's the key.
So let's start with the foundation. What is MedGemma 1.5 and why should a developer even care?
At its core, it's an open, multimodal model. It's built on the Gemma family, but has been specifically tuned for both medical text and medical vision.
And the initial key selling point is just how accessible it is.
Right. It ships as a 4B instruction-tuned variant, and that size is critical. It's small enough to explore on a single modern GPU while still packing some serious capability.
Which is a huge deal. Historically, the really impressive models in the space needed massive infrastructure, which immediately put them out of reach for individual prototyping.
Yeah, the 4B variant really democratizes the entry point.
Okay, so that smaller, more accessible size is paired with some significant feature upgrades. We're talking about direct support for those complex data types we mentioned earlier.
CT and MRI volumes, whole slide pathology, WSI, and much stronger longitudinal comparison capabilities for things like chest X-rays.
We need to clarify what that high-dimensional support actually means in practice, because this is where developers often make the wrong assumptions.
Yes. It does not mean the model ingests a DICOM file and just scrolls through it like a radiologist on their workstation. That's not how it works.
So what's the right mental model to adopt here?
The model reasons over visual tokens. In practice, this means you, the developer, have to feed it a curated set of slices or patches, a sequence of 2D images, really, alongside your text prompt.
So the input quality is now your responsibility.
100%. The model is tuned to interpret and reason over that bundle of encoded visual information you give it.
That distinction is absolutely crucial. And if the input quality is our responsibility, then the environment where we run it becomes critical. This brings us to the next point. Offline capable changes the workflow.
If you're serious about building tools in healthcare, running locally is, well, it's the whole ballgame. It fundamentally shrinks your iteration loop.
Right. No API latency, no recurring cloud costs.
Exactly. But beyond performance, it gives you deterministic logging. You can easily replicate failures precisely as they happened. And most critically, it lets you keep sensitive, de-identified samples contained within your own environment.
That control is the single biggest reduction in third-party vendor risk you can have.
No question.
Okay, so now that we know we can run it, let's explore what it can actually do. Let's frame this around practical tasks. Forget the academic benchmarks for a moment. What are the use cases?
The model excels at summarizing findings, producing careful, structured text, and performing comparisons.
Diving into the specific imaging capabilities, let's start with the most complex one, CT and MRI volume reasoning.
Okay, so the workflow is pretty much the same. You select and provide multiple slices plus a specific question, and the model replies in text. This is designed for assistance.
Assistance, not diagnosis.
Absolutely. Think triage support or labeling data for research or HUA checks. I have to emphasize, it is explicitly not a system where you feed it a DICOM file and it spits out a final diagnosis.
And for a whole slide pathology, or WSI, you're dealing with these gigapixel large images where the signal you care about is super localized. How does MedGemma handle that scale?
It supports really the only workable pattern, which is patch extraction. You break the massive slide down into thousands of manageable tiles, and then you reason over a curated set of those diagnostically relevant patches.
So you need a strong pre-processing pipeline to make sure you aren't just sending blank background tissue to the model.
You got it. That's half the battle.
I really love the specialized focus on longitudinal chest x-rays? That's such a common clinical scenario where comparison is everything.
This is a standout area. The model was specifically trained to talk in terms of progression, stability, or new findings when you give it a current CXR and a prior one.
So it's not just describing two images independently.
No, and that specialized training makes it significantly easier for developers to build comparison tools that speak the language a clinician actually expects.
And, we often focus on the imaging, but there are two seriously underrated wins here. The first is anatomy localization.
Yes. The model has improved capabilities to draw bounding boxes, which allows for region-aware reasoning. You can ask specifically about, say, the right upper lobe, and the model can ground its response geographically.
The second underrated win is lab report extraction. This feature it saves weeks of grunt work.
It really does. If you have ever fought a complex medical PDF or a digitized fax with regex, trying to pull out blood values, units, and labels into structured JSON, you know the pain.
Oh, yeah.
This feature dramatically simplifies that. But, and this is a necessary caveat, you still need to validate those outputs like your job depends on it.
Because in this field, it absolutely does.
It does.
Okay, let's move to the proof. The benchmarks and the fine print. Benchmarks are always a rough forecast, but the numbers here signal a pretty major shift in utility. What was the most impressive leap you saw?
Well, if we look at where the 3D reasoning improved, the gains were tangible. For CT findings, macro accuracy moved up by a decent 3 points.
Yeah.
But the MRI findings, they saw a truly massive jump from 51.3 to 64.7.
Wow, that's a big jump.
It suggests a much stronger baseline for a notoriously difficult modality like MRI classification.
I was most surprised by the low-level visual grounding. Anatomy bounding boxes measured by IOU improved dramatically. What were those numbers?
The IOU metric went from a dismal 3.1 to 38.0.
From 3 to 38.
That is the definition of going from barely working to genuinely useful. That improvement alone tells you the model is far better at visually knowing where things are, which grounds all of its reasoning.
And what about for EHR question answering?
For EHR-QA, the accuracy saw a major lift from 67.6 to 89.6. That's a very strong performance for that kind of retrieval Q&A.
But the fine print is crucial. Where do the numbers not save you?
Well, the model still has specific weaknesses. Some complex visual Q&A styles can be harder to answer accurately, and overall report generation isn't automatically a solved problem just because other metrics improved.
So the core takeaway is?
It's an incredibly strong base model, but you should absolutely plan on adaptation and maybe even fine-tuning to perfectly fit your niche clinical use case.
This naturally leads us into the thorniest subject, compliance. You often hear people ask, is the model file itself HIPAA compliant?
And the immediate non-negotiable answer is no. There is no shortcut. Compliance is a property of the entire system, your processes, and your contracts. It is not magically baked into a model file.
So how does running Inference locally actually help our compliance efforts?
It gives you complete control over the data perimeter. If you run MedGemma 1.5 on your own managed hardware and ensure that protected health information PHI never leaves your secure environment, you eliminate the massive vendor and transfer risks that come with sending data to an external API.
But that control comes with enormous responsibility.
It does. Which brings us to the practical checklist for anyone prototyping. You have to deal the operational hygiene.
Like what, specifically?
Strict data handling. De-identify when you can. Enforce least privilege. Keep meticulous audit logs. You need storage hygiene, making sure you don't leak images or prompts via caches or notebook history or system logs.
And human review is mandatory.
Mandatory. Treat outputs as high-quality drafts that always require clinical correlation and a second reader check. And finally, disclosure. Never, ever present MedGemma 1.5 or any LLM as a diagnostic device.
So local makes compliance achievable, not automatic.
Perfectly put.
Okay, let's shift gears entirely to the mechanics, getting it running. What are the basic hardware expectations?
The 4B parameter count is friendly, but you still need a CUDA-capable GPU. It's just non-negotiable for the vision pathway.
And if you're just on simple CXRs, life is pretty smooth. But the moment you tackle CT volumes or whole slide imaging, the memory requirements spike. And they spike fast.
They do. This is a subtle trap. Those high-dimensional workflows require substantial extra RAM just for the preprocessing. You'll often find that the time spent loading CT slices or extracting WSI patches dominates the runtime, long before the model even generates a single token.
So what's the required software stack?
You need Python, PyTorch with CDA support, Transformers version 4.50 or higher. That's required for the Gemma 3 support, and Accelerate. And if you value reproducible results, which you must in this domain, pin those versions.
And the canonical model ID to download is Google MedGemma 1.5 4B on Hugging Face.
Yeah.
That's your starting point.
It's the key. And my advice is, if you are aiming for local operation, start small. Get a chest X-ray demo working to stabilize your environment before you even dare tackle the complex volumes.
Okay, let's walk through that fastest demo using the Pipeline API. This is the hello world that proves local operation is possible.
First, install your dependencies. Pip install DICOM transformers accelerate. Then, you load the pipeline, referencing that model ID.
And this is important. You need to specify torch type, torch.bfloat16, and device CUDA. We use bfloat16 here to cut down on memory usage, which is crucial, while still maintaining precision.
Exactly. Then you structure the input as a message array. The content is a list containing the image object in your text prompt, something like describe this X-ray in plain language and list key findings.
And once that runs, you've proved the concept.
Yep. Then you can graduate to the direct model API for better control over things like batching and prompt templating.
Now for the real intellectual challenge, vision input and the pre-processing reality. Why does reasoning over 3D data feel so sort of counterintuitive at first?
Because again, the mental model is wrong. You're not feeding it a volume to scroll. You're feeding it a sequence of images, and the model reasons over the combined set of encoded tokens from those images.
So the model cannot see what you do not feed it.
It cannot. This means the quality of your pre-processing layer is arguably more important than the quality of the model itself. Slice and patch selection isn't a small detail. It is 90% of the work MedGemma 1.5 doesn't do for you.
Which leads to the 3 immediate constraints every developer will hit.
Right. Selection.
Yeah.
Which slices are actually relevant? Ordering. Does a sequence matter for my task? And the big one, context budget. How many images can I fit before I run out of model capacity?
Fail to control those, and you just spend all your time debugging bad input.
Let's detail the pragmatic 6-step pipeline for handling a CT or MRI volume locally. This is where most of the work lives.
Okay, step 1, load the DICOM series into a volume array. 2, de-identify and verify. 3, normalize intensities and apply the right windowing soft tissue, bone, whatever.
Step 4, select the key slices that cover the anatomy you care about. Step 5, convert those slices to the specific image format the model's processor expects. And finally, step 6, prompt the model with a task-focused instruction.
And that prompting strategy in step 6 has to be sharp. You need to be specific. For example, list suspected findings with confidence. If you can't assess something from these specific slices, explicitly state that.
You're telling the model what to do, but also what to admit failure on. It's a critical guardrail.
Moving to specialized strategies, let's look at WSI pathology again. The baseline patch strategy is critical here.
The first step is to build a tissue mask. You don't want to waste context on white background. Then use sample patches at a consistent magnification, batch them up, and ask a focused question for each batch.
But a single slide requires many batches, so you need robust aggregation.
Yes, you aggregate those batch summaries into a slide-level impression, but you have to build a safety check, a guardrail. If one batch summary claims there is necrosis and another batch claims the tissue is normal, the system can't just average that. It needs to flag that contradiction for a human.
And the other specialized strategy is for longitudinal chest X-rays, where a MedGemma 1.5 really excels.
The prompting pattern here has to force comparison to use that specific training. The simplest effective pattern is structured labeling.
So you'd say something like, image A is prior, image B is current. Compare B against A. Output the comparison as one of 4 labels: new, improved, worsened, or unchanged. Then provide a one-sentence impression. This strict templating prevents the model from just describing 2 images separately.
Okay, finally, let's address laptop limits and the QA loop. Everyone asks if they can run the 4B model on their personal machine using something like a llama or GGUF quantization.
For purely text-only experimentation, sure, a laptop can be fine. But for the real CT and WSI workflows, you will hit a wall and you'll hit it quickly. A dedicated GPU is still necessary.
Why is that?
Because the vision pathway and just the sheer memory bandwidth required for those intense pre-processing steps demand it.
And if you do find a quantized build, you have to verify 3 things. Right. Is it the full multimodal instruction-tuned variant? Does the quantization maintain quality for your specific task? And does the runtime actually support visual input? Don't assume that convenience hasn't come with a major fidelity hit.
Which brings us to the final and maybe most crucial piece of advice. Stop asking the model to be a doctor. And start asking it to be a careful, highly specialized assistant.
Exactly. Let's look at some of those doctor-friendly templates. Instead of saying, "What's the diagnosis?" you ask for a findings summary.
So describe visible findings in bullet points. If uncertain, say so. Do not guess history.
Or for differential suggestions, you add caution right into the prompt. List possible explanations, tag each as common or rare, end with a mandatory sentence. This is not a diagnosis and requires clinical correlation.
And for data extraction.
Always demand strict, verifiable JSON output. It makes your downstream systems so much easier to build.
So the most practical path forward is what you call the lightweight two-reader workflow.
Yeah, you run the model on a fixed case set, have a human score the factuality and usefulness of the output, and then you cluster the recurring failures.
And only after you've identified those systematic failures and adjusted your pre-processing or prompts should you even consider the expensive path of fine-tuning.
The closing advice is simple. Pick one modality, start small, collect 5 ugly failures, and turn those 5 failures into reliable, non-negotiable tests for your prototype.
So what does this all mean? MedGemma 1.5 offers a powerful and pretty straightforward local starting point for serious medical prototyping, provided you respect the input constraints and you implement the compliance realities we discussed.
It moves the needle from theoretical promise to a practical single GPU toolkit that's ready to use.
Okay, so here's the final provocative thought for you to consider. We've established that the model can only reason over the specific slices or patches you feed it. The real engineering challenge moving forward is not the model itself.
No, it's designing that smart pre-processing layer that reliably selects the most diagnostically relevant information while managing that context budget. So the question is, what selection criteria, like integrating an existing segmentation map or using anatomical filtering, what would you focus on building first to solve that input problem?
That's a great question to chew on as you spin up that local environment. And if you do build something, publish your honest learnings because the community desperately needs more transparent evaluations over simple screenshots.